Welcome to today's show. So today we are going to do something really exciting, a really low-level project. We're going to code our own memory allocator, and we're going to start the code in just a few minutes. I will just start by showing visually how this is going to work. So we start out at this point by reserving 1 gigabyte of process memory. And what we do is we divide this memory segment, which I call the heap, the dot in front. So we will have a lot of these different sections, so to speak, all the way up here. So each of these segment is 4 bytes each. Or 32 bits. And I will be calling these words. So one word is 4 bytes. And that is the least amount of memory that can be allocated. So this first one will have index 0 and 1 and 2 and 3, all the way up to around 250,000. So this is our heap. This is what we have to play with, so to speak. All right, I'm gonna clean this up a little bit before we continue. All right, so what is going to happen if we want to allocate, say that we need 8 bytes of memory for something. That means 2 words. There will be a very tight overhead for this memory allocator. So if we allocate 2 words, what will happen is, so this first word will be the header. So I denote this by an H. And these 2 others will be the memory that this allocation contains, the memory that we can use. And I denote this by this purple color. All right. So let's start by defining how this header should look. So this header is 4 bytes. And if we do something like, let's do this. An arrow down here. So this is a zoom in of this header. So every allocation will have its own header. And this contains 3 different things. This to the left here. Let's make this a green color. Something like this. And this will be something which I call the W. This is the number of words that follow. So in this case, it will be 2, since we're allocating 2 words. Then the next one, which let's make this yellow. This is a 1-bit thing. Maybe I should type this. So this right here is 30 bits, the green part. Then we have this, which is 1 bit. And this is a boolean. So let's do this. This is a boolean which I call allocated. So this basically means that these words that follow this header, they are either allocated if it's true, or they are not allocated if it's false. So when we do an allocation, this becomes true, and when we free that memory, this becomes false. Then we have one more thing. So this second bit, this is also 1 bit, and that is reserved. So this is not used at the moment, at least. But we have 1 bit in the header that we can play with, so to speak. This green part right here, that is the W, the number of words that follow this header. This yellow part is the allocated boolean. Is the following words allocated, or are they deallocated again? And then we have 1 bit reserved. So this 1-word header is all the overhead that exists in this allocation. So if we were to make another allocation, let's say we want 5 words, then we start out with an additional header, like so, and then we follow 1, 2, 3, 4, 5, and so we continue. So we can use almost all of this 1 gigabyte space. The only overhead is 1 word per allocation, which is quite good, I think. So if we were to translate this header into C code, we would do something like, and what does it contain? Well, the lion part of it is this W, the number of words. So then we have the bool allocated, one bit, and then I will make a type declaration. So we'll do something like type def struct tact s header, and this data type will be called header, like so. So it's a very simple design. One small header, then the allocations, and then another header and the allocations. And if we want to, let's say we want to free, let me just make this a little bit smaller. let's say we want to free this first allocation. So we will zero out these two, and that's strictly not necessary, but since we want to have some memory security, I will still do that. And the only other thing that we will change is we will set allocated. Let me go back to this. Allocated equal to false. So if we were to do a third allocation in this instance, and we want to allocate, say, one word, the only thing we will do is we want to change this W. So currently the W is equal to 2 because the whole is 2 words deep. So we will change this value of 2 to 1. So if we were to do this, then this part will be part of the new allocation. And then we will change this allocated false back to true. So every time we do an allocation, we will traverse this memory heap and find a suitable hole. And if we don't find a hole, when we come to the end right here, we will put the allocation there. And we will of course do a check if this we have here is big enough for that allocation. Otherwise we will return with a no mem error by setting the let's see, the R number, which is a global variable, to this, and then we will return 0. And if the allocation succeeded, we will return a pointer to this space right here. So it will work the same way as malloc. We will do something like, let's say we have an int 8 and let's call this string or something, and we want to allocate, say, 12 bytes for this. Then we will do str is equal to, and we cast it to an int 8. So int 8, and this should be an int 8 star, by the way, since it's a pointer. So int 8 star, and the function name will be called alloc, and then we just give it 12. So it will work with the same syntax as the regular malloc, and return a pointer to that mem space. And I will also create some aliases. So I will have something which is called kalloc, which will take a number of kilobytes to allocate, and same with okay, maybe malloc is not so well. Let's say we do alloc k and alloc alloc m. number of megabytes. So we will be able to allocate, we can make one allocation for almost 1 gigabyte if we wish to, or several big allocations, and everything will be very fast. We will code almost all this in C, only one little tiny thing, like a 5-10 minutes code of assembly in order to reserve this first block of mem space. And each of these allocations or holes will be called one block. So a block can be like 1 word in size, or it can be 250,000 words in size. So that is the general idea of this, and it looks pretty complicated when you look through what I have drawn here, but it's not really very difficult to understand, I think. And we'll also have a free, I'm not sure what I'm going to call it, but it will work the same way as the free in the C library. So you give it a pointer to the first memory part of the allocation, and it will free that and create a hole. And possibly I will also make some realloc, which can change the size of a existing allocation. But I'm not sure if I'm going to do this. And the good thing about this, especially for a lot of you guys, is that this is pretty fast to create. I think it's going to be 2-hour episodes to code this thing. And it's a very, very, very good project to have on your resume. So putting in those 4 hours of work would probably land you the job that you want to have. And I also intend to replace the regular malloc with this in all of my code moving forward, because everything of this is done in userland. Usually when we create a memory allocator, we will either use the sbreak system call to allocate memory, and I think this will run equally well on Windows if you use a POSIX compiler like Cygwin. It will run in Mac OS and of course in Linux. So yeah, let's get started. Sup guys, welcome to today's show. So today we're gonna create our very own memory allocator. And let's start immediately. I haven't thought of a name for this project. Alloc for now. I'm gonna use bash bs to create the project, and you can find this in the repo if you need. So let's create the alloc project, and we use the default C template. I will set this to my home and open it up in VS Code. So let's see, here we have a alloc. And I haven't prepared anything in advance for this project, so we will see how it goes. I have some general idea in my head though. Alright, so let's start as we usually do by changing up few things. Let's rename those aliases. So this is 1 byte, 2 byte, 4 byte, 8 byte, and I also want to have one for int 128. And since we're probably gonna use quite a lot of void pointers and stuff, let's create one for void as well. And I'm gonna define a data type which is called header. And we're probably gonna cast quite a lot to that as well. So let's create an H for header star. And let's type def an unsigned, let's see, bit int 128 to int 128. Let's also create something of the void type, which we are going to call let's call it heap. All right, and the header is going to be quite simple. So we are only going to use 32 bits. So let's create a struct and not any struct. This will be a packed struct, which I'm going to call struct header. So this will contain a 30, let's see, let's say it's a 30-bit integer, which will keep track of the allocation, the number of blocks, or number of words rather. So let's create a word data type as well. So an int 32 will be a word. So we will have word W, and this is going to be 30 bits. And we are also going to have a bool let's call this alloc. So this says if it's allocated or not, and this is 1 bit, and then we will have 1 extra bit which is reserved. So let's say this is also a bool, which we will call reserved 1 bit, and this is going to be unused. So let's see. I think we can put it right here. And we need to define what an unused and what a packed is. So let's do that. So packed is going to be an attribute. And an attribute basically tells the compiler how it's going to handle different things. And the syntax is quite weird, like this. So that's why I like to make my own definitions. And we will also have an unused. It has the same weird format and unused. And that's only to tell the compiler that it shouldn't give warnings and stuff when we don't use this. And also to indicate our intent to anyone reading this code. All right, so let's type def struct. I'm not sure if we should have packed here as well. Let's try s header, and this will be called header, like so. And we're gonna create a mem space, which is going to be well, it's going to be of the heap data type, so extern heap, because we're not going to define this inside of this file. And this would be a pointer to a mem space. Like so. Let's see if this compiles. We might have to change it up a little bit. Expected on line 12. Shouldn't have these. Okay, compile without warnings or anything. That's good. So far, so good. Now to the tricky part, perhaps. I want to define this mem space as 1 gigabyte of memory. And that's quite a lot. Maybe we should make our lives a little bit easier. No, let's do it like this for now. So we need to do this in assembly, I think. Otherwise we don't have that granularity, that level of control. But there won't be many lines of assembly. So let's call this our heap.asm. And how do we define this? Well, it's going to be 32 bits. And we will make a definition. Let's say this is the heap size. So if we do 1024 times 1024, then we have a megabyte. And then we do times 1024 again. So now we have a gigabyte, and we divide this by 4. So now we have the number of words, or number of 32-bit integers that we need. So now we define our actual mem space. and we want to export this as well. So let's do global memspace. So first up, we need to define our heap size. So let's say the heap size with a small h is equal to heap size with a big H. So now we want to reserve double words, that's integers, and we want heap size number of words. And we want to have let's jump this out one step, and we want to have a section for this heap, and let's call it .heap. And this should be read write. I think this is the correct format. Let's try assemble this thing and see what it says. So we will do nasm-f elf, and we take the heap.asm. Okay, it didn't like the read write. Uninitialized space declares non-BSS, zeroing. Okay, so we got a few warnings, but not an error. And it takes a little while, which is a good sign, because it's gonna have to create 250,000 of these words. I wonder if we can specify that this should be treated as a BSS section. In that case, it doesn't have to put all those zeros inside of the actual file. Let's see, I think there is a man page for this. If we go to anasm and let's see. Let's search for elf sections. Okay, so this alloc, we want to set that to false, but how do we do that? Or wait a second, BSS is alloc. They can be negated by prepending no. Okay. Alright, so we want alloc. We don't want exec, we do want write. Is stored in the disk image. Okay, so prog bits should probably be false, right? Ah, that's right. That is what defines a BSS-like section. And we can put in an alignment as well. But it succeeded, but it's very huge. Let's check it out. If we can we read elf.o file? Yes, we can. And we want to check out the headers. Always forget which one it is. L is for program headers. Let's create a temporary text section just so we can see what's going on. So this will be not global, this will be start. And we need to export start. Let's update this thing. So alloc should be true. Exec should be false. Write should be true. Prog bits should be false. No prog bits. And align should be 4. All right. So let's remove this .o and let's run anasm again. Unknown section attribute no prog bits. Except for a line, they can be negated by prepending no. No bits, okay. All right, that went a little bit faster. And this file is very small, which is good. And if we were to link this thing, so heap.o, and we create temporary file. Can we run this without a crash? No, it will probably crash because we don't have any exit code. Yeah, but we should still be able to get some information out of it. So if we were to do read elf-h tmp. Okay, we have 5 section headers. We have 1 program headers. Okay, so this is our heap. And this is our mem size. If we were to take the decimal version of this and we were to let's let's do this. So we divide it by 1 megabyte. Yes, it's 1 gig in size. Great, so it works. I'm not sure about the alignment. Oh, maybe. This is a 4, isn't it? 1, 2, 4. No, it's an 8. Why is it 8? Well, it's not a big deal. The important thing is we were able to create this mem space. So let's remove this text section and this, and let's see if we can link this thing to our C code. Let's also do something with it. Let's say we create an int 8p, and p should be equal to memspace, and then we change the first character into x, just so we see if we can do stuff with it. And let's go to our makefile. So we'll have an heap.o, which requires heap.asm, and we're going to do nasm-f elf heap well, the source. So let's see, when we compile this thing, we want to use the heap.o as well. And let's change this to C23. All right, let's see what we get. Okay, it complains about that. Let's create this section as well then. Okay. And what happens when we run this thing? Does it crash? It does. Why though? Because it is a read-write memory space. Let's go to GDB and just see what's happening. So TMP, and we go to, let's see, we call it alloc. So let's just prepare the debugger. And let's define our f function, target exec, and target exec alloc, symbol file alloc, and then we'll define xx as x30i, VIP -20. These are just my default settings. And let's also define clear, yes, and we should do clear and alright. So let's start this thing and run. Oh, F, run. So here it is where it crashes. We try to move into whatever is inside of EX 58. So inforeg EX, and EX is 0. Maybe we need to export a pointer instead. So let's do section data. This will be a lock, no exec write prog bits. So let's call this underscore memspace. And let's put the real memspace here. And let's make this a pointer instead. So we will define a double word, and the contents should be the address of memspace. Right? And now it works. Very, very nice. Very, very nice. All right, so the hard part is done, I hope. So no more assembly, and the make file is done as well. So now we can start to create this allocator. Alright, so how do we do this? Well, we need to have an alloc function to begin with. And it's going to work pretty much like the regular malloc. So it's going to return a void star. Let's just call this alloc without an M. And it's going to take a number of bytes. So int 32. Let's see, is that enough? Yes, it is. So number of bytes. Okay, so let's create this function, alloc, and it's going to take an int 32 bytes. And we need to convert this bytes to number of words because that is the smallest amount we can allocate. So let's have a words. So first let's check if, or we can do like this, by the way. So if bytes is a multiple of 4, in that case we can just take bytes divided by 4. And if it's not, we need to take bytes divided by 4 plus 1. So for instance, if we want to allocate 7, that means that we will need 2 words, because 2 times 4 is equal to 8, and that has room. Which means that 7 divided by 4 will be 3 in this case, because we don't do any decimals. And 3 plus 1, no, I mean this will be 2. Let's see, 8 divided by 4 would have been 2. So 7 divided by 4 will be 1. That is the case. And if we add 1 to that, we will have 2, and that is what we want. So this is good. So now words contains how much we want to allocate. Now we need to find a hole for this. And if this is the first allocation, we might want to handle it differently. Perhaps not. We will see later on, but for now we will do that. So let's see how to do this. I want to try something. Is it possible to do, instead of a regular if statement, can we do something like this? So if, let's see, well, let's create a header first. And we need to create some intermediary variable. Let's call this mem. So mem should point to the mem space. And header should point to mem. And now we can check if header and its W, that is this part, how many words that follows. And if that is 0, it means nothing has been allocated yet. In that case, what do we want to do? I'm not sure if we can use this syntax, but I want to try. So let's have some code here. For now, I will just exit. And let's also print something empty. And otherwise, we print something else. Let's see if this compiles. No, okay. Expected expression before. What if we put a parenthesis here instead? Huh, that actually worked. And if it's not empty, so that will be, let's see. It did not go to the else clause. What if we were to manually set header v equal to 1? Yes, it works. So are we going to use this syntax from now on instead of regular if statements? It's quite ugly, isn't it? But quite cool that it actually works. This is just an example of how much freedom you have when you code a language like C. Alright, so let's remove this stuff. Okay, so let's see. If this is the first allocation, and we know the number of words we have, we want to check if we have room for these words. So maybe we should create some definitions. Let's say max words. So how much is that? Well, it's gonna be 1024 times 1024. This is 1 meg, 1 gig, divided by 4, and we get the number of words. But we need at least one header as well, which is 1 word in size. So let's do -1 like so. So these are the maximum number of words. So if words is more than max words, then we want to return an error. And we need to somehow be able to return different types of errors. So let's say we have an error which is no mem. Let's also create an alias, return error, and it takes an X. And what do we want to do? We want to, let's see, we want to set the error number global variable to the error at hand, and then we want to return 0. And this R number is included in this file. So if words is more than max words, we want to return an error of error no mem. Otherwise, we want to make this allocation. So maybe we should have a different function for that. So something like make allocation. And we want to give it the number of words and the current point in the heap. And since this is a new heap, it's going to be whatever the header basically. So if this returns 0, we want to propagate this error. So let's do let's see. I want to see what this R number, how it's defined. Well, let's do an int32 and let's make the compiler complain if this is not the right thing. So we set ret equal to this and we propagate the error. No, this is not good. Let's do this instead. We'll set our mem variable to make allocation. We pass the words and we pass the header. If mem is 0, we want to propagate the R number. Well, let's just return R number in this case, because we cannot really set R number to R number. That doesn't make sense. But if we have a result, so it will return the pointer to this new allocation, or the first byte of the allocation, and we want to return that. So we'll do this. Right, and this function make allocation is going to take two things. The first is the number of words, and the second is the header. So we'll have a make alloc words and header. We're going to have a return value. And we want to set the header's words to the number of words, which is this. But first we want to check if this is really, if we have enough space. So we can do some pointer arithmetics, because mem space is the first byte of the mem space. So we can calculate where this header is. So how many words in are we? So this can be equal to, or this will be bytes in, by the way. So if we take the address of header and we subtract the address of the mem space, then we are left with a number of bytes in. So then we can calculate the number of words in. Maybe we can do this. So words in will be equal to bytes in. Divided by 4, and just to be safe we can add 1 as well. So now we can check if the words we want to allocate is more than the difference between max words and words in. Then we don't have enough memory to do this. So in that case, we can return no mem. Otherwise, we should do the allocation. So we'll set the number of words to the number we want to allocate. And what else do we have? This alloc should be set to true. To indicate that these are reserved. And now we need to calculate the pointer address of the actual mem space, and that is the header plus 4. So ret is equal to the void header plus 4. And we return ret. Simple enough. And if you wonder why we do this check here, and we do the check here if we have enough memory, that's because this function may be called from somewhere else. Maybe we create a realloc function at one point. Then we want to have checks and balances in order. All right, let's see if we can allocate these 7 bytes. Unknown name header, okay. This should be header. Oh, this should be word. Assignment 2 void star from int. Oh, this should be word. Max words undeclared should be max words like this. Ret are undeclared. Should be like this. And we should not return the error number. We should just pass it along. which means that we should return a 0 instead here. Okay, compiled, but we get a 0. Wait a second. The return R thing does two things, so we need to put this inside of here. Okay. Those macros can fool you a lot sometimes. So let's check all the places where we use this return error thing. Same here. Okay, we get a pointer back. So our allocation succeeded. Okay, so now we are able to make an initial allocation. So we need to add a possibility to make several allocations, and then we want to make a free function, and then we want to make it possible to allocate memory inside of holes that have been freed. But as of yet, everything works. So we'll be right back after this. Sup guys, and welcome back. So before the break, we managed to be able to create an allocation, but only one. So now we're gonna improve this program and make it possible to do more than one allocation. And perhaps we're gonna generalize this if statement a little bit. Alright, so let's see. Currently we only check if the first block contains a 0. So 0 words in that block. That means that it's the first one, and then we currently handle it like this. But it would be better to create some function which locates the first available block and returns that block. So let's call it find block perhaps. And it's going to return the header of that block. So header find block. And I think I'm gonna call this find block prime actually, because I'm gonna have a macro which calls this thing. So what is it gonna take? Well, we need the current header of the current block, and let's see, is that all we need? We could use some kind of a counter. It's not strictly necessary, because we can do pointer arithmetics like we did in the make allocation function. but I think I want a counter in this case because it will make things a little bit easier. So let's have a word here which counts the number of words that we have passed. That way we know when we get to the end. All right. So let's see. Maybe we should do the macro first because I want to have a function like macro, which is called find block without a prime, and it's not going to take any parameters. And the only thing this is going to do is call find block prime, and it's going to give the first possible block, which is the mem space. So we need to cast this into a header, and we have the mem space. So this is the first block. So that's where we start searching, so to speak. And at this point, we have passed 0 blocks, words. All right. So let's see how we make this function. So we do header find block, and we have a header, and we have a word. And what we're gonna call this one? Let's just call it n. Okay, so what do we need to check here? First of all, we want to check if we have passed too many. So if n is more than max words minus 2. And why minus 2? Well, if we want to use this to find, never mind, maybe we don't need to do that. Let's just do it like this. Because we could do it the way I showed, because I was thinking the header takes up one word, and we need at least one word allocation, so that's why it's 2. But I'm gonna need another check as well, so let's do that there instead. So if this is the case, by the way, I wanna fix one thing. This return error function, let's do this instead. So we do, and we open a block, then we do this, and then we return the thing. And then we do the while false trick. So the while false makes this run only once, so it's a loop, but it will not loop, it will run only once. And then we get this code block right here, which means that we can remove this and this, making our code a little bit cleaner. Then we can do the same here. We can return the error of no mem. Alright, so that's this thing. So we will have a couple of different possibilities. One is the current header's W, so the word count, is 0. And that means that we are at the last block. So let's do our new if statement syntax. So if the header W is 0, then what do we want to do? Well, in this case we are going to use this block, but we do need to check if we will write. When we use this function, we need one more argument, because we need to specify how much we need to allocate. So we need a second word right here. And we need this here as well. Let's put it here. So this X is how many words we wish to allocate. So we will put it right here. What are we going to call this? Allocation. All right, so if the number of words we have passed plus the allocation, maybe we can do it right here instead. So if n plus allocation, and here we can do what I first thought. If this is more than max words minus 2, so the current number of words that we have passed plus how much we want to allocate. If that is more than max words minus the header and at least one word allocation, then we return error no mem. So this is probably the only such check we need. Alright, so if this is 0, maybe we can create a bool, okay. And okay is false as default. And if this is 0, so we're at the last block, and we know already that we have room for this allocation. In this case, we can just maybe we can just do this. We set OK is equal to true. I guess we can do that. We do, however, need, let's see. Right, we can do this. So if it's 0, then we're okay. Otherwise, we want to check we want to check that this is, no, we don't need to do that. Let's see, how is this structure? We have the W, which is the number of blocks that follows. We want to see if they are alloced. So if we're at some block that has been allocated and deallocated, which means that W is positive, but this is false, so it's not allocated. And we do also want to check if this block has enough room. So if this W is more or equal to the allocation we want to do. So in this case, there is a hole, and the hole is big enough. In that case, OK is true. guess these are the only two things we want to check for. So maybe we can do this a little bit cleaner by doing OK is equal to true, or it's equal to true if this case as well. And otherwise false. So either it's 0, the W, that means that we are at the last block. And then we can set it as true because we have already checked that it fits the entire space. Otherwise, we check if it's been deallocated, and if the hole is big enough. In that case we set it to true, otherwise false. Okay, so if OK is true, then we wanna make this allocation, or the function name is called find block. So in this case we have found our block. We want to use this for our allocation. So we can just return the header. And otherwise, we want to go to the next block and try this again. So we need to find the next block. Let's create a void mem. And let's create a header prime. And maybe also a word n prime. So we set mem equal to the current header and we want to jump forward header W, that's the number of words. And then we should land on the header of the next block, which is where we want to be. So we can set our header prime to the header cast of mem. So that's the header of our next block. And we want to set n prime equal to the current n plus this number of blocks. And now we have all we need, so we can simply return, and we do a recursion, and we do header prime, we push through the allocation, and we do n prime, like so. And if we were to come here, which we shouldn't, but we never know, then we will return our unknown, which we need to add. All right. So let's test this function. Let's start by printing the address of the mem space. And then we can print, let's do this, header p, and we set p equal to find block, and let's say we want 500 words. If we don't have a p, then we want to print error this. Return -1. And otherwise we print that address. So if this works, both of these addresses should be the same in this case, because we want to allocate at the first position. All right, let's see if this compiles. Max words should be with a capital M to indicate that it's the constant. It compiles, and we get the same one. Good. And what if we do an allocation first? Then we should get a different result, hopefully. Oh, I named both P. Let's call this header instead then. So let's see, we allocated this. And mem space is this. Let's just see how much difference this is. This should probably be 4 bytes, which is the header. Right, good. And our next block is 1e. And how much difference is that from mem space? So it's 2 bytes from the mem space. Is that right? Because we have one allocation, that is one header, and we have 2 words. So that's 3 words times 4, that's 12. And then the next one should be, so no, it's not calculating properly, I think. Why is it 2? Maybe I confused bytes and words. So we have memory is the header plus, right, plus words times 4. Because a word is 4 bytes. Let's try this again. So this is the next block. And if we compare that to mem space, it's 8. And this is what we allocated. So this is the first part of the memory space. So if we take this minus 4, we get the address of the header of that block. And that's the same as mem space, so that is correct. But this is just 4 bytes past this. Let's see, so here we take the current header minus mem space. So how far in are we? This is 0 in this case. 0 divided by 4 is 0, I guess. Plus 1. Let's just double check that. 0 divided by 4 is 0, right? So we set the words to no, words is what we pass to this thing. Make alloc words, and words is, in this case it should be 2. So from the first position, jump 2 words. So we have the header, and then we have 2 bytes of mem space. And then the next header should be here, and we're here 1, 2, 3 it should be. Alright, so let's do plus 1 here. So we take the header into account as well. So our new block minus our mem space is 9 bytes, which shouldn't do 1, then we should do 4. It's 1 word. Alright, so now it works. Now we want to change our allocation function. So we use our new one. And instead of using, let's see, we can still have this, but let's remove this, and we set header equal to find block and we give it the number of words we want to allocate. And if we get an error, we will just pass that on. Like so. And then we don't need to have an if statement here. Still want to do this check, and we allocate based on the current header. And that's probably all we need to change. And the result should be the same at this point. Which it is. Good. But now we should be able to do two allocations. So let's see. Let's do a P2 as well. P2 is equal to alloc, and we can remove some of this though. So let's see. First we allocate 7 bytes. Then we allocate 2 kilobytes, say. And let's see what we get. So this is our second one. And it's still 3 words away, which is true since this first allocation is the same size. And if we were to do one more, it should probably be 500 there instead. Maybe we should try that too. So this should be 2 kilobytes from this plus the header. Which it is. Nice. And by the way, not exactly 2 kilobytes, 2000 bytes to be precise. 2 kilobytes is 2048, but it works. It works very well. So now we can do multiple allocations. Nice. Let's also create a show function which prints out the entire heap. So let's say void show. Maybe we can do this. Show prime, and we give it a starting point. And then we do the same magic as before. So we do show of nothing is show prime of mem space. And I will make this pretty simple. So void show prime. We have a header as a starting point. So let's see. We can do a while loop. Let's create another header as a pointer, and as long as we have a PW, we will continue looping. Maybe we can do a for instead. So P is equal to header. We loop as long as we have a PW. And at each iteration, P let's do this. Mem should be equal to our current position plus number of words plus 1 times 4 bytes. And then we set P equal to mem. Let's also have a counter. Maybe we can set it to 1. So every time we iterate, we will have one allocation with a number. So the first is our N, and then we have our W, and then we have a string. So we check if this is allocated. If so, we say that it's allocate, otherwise free. All right, let's see if this works. So we should just do show. Maybe we don't need to print these. Oh. $48. This should be an H. Two allocked words, 500 allocked words, 1 allocked word. All right. So we have made quite good headway. Now we can not just allocate one time, we can allocate as many times as we wish. We have generalized our allocation routines, so it gives us a little bit more freedom. And we can print all our allocations. Our next step is going to be to be able to free memory. And then we are pretty much done, perhaps. Well, we'll see, won't we? So, if you like this episode, please like and subscribe, and hit the bell button so you know when the next one is released. And thanks for watching. Thanks for today. Did you know that I made a book about computer networking? You will learn how the internet works and how everything works under the hood. It's a complete beginner's course, but it has some advanced elements as well. And you will learn network design and network security and all different kinds of stuff. For more info, check out books.drbirch.com. That is books.drbirch.com. Thank you for your support.